Well, thank you all for coming. I think we'll get started now. We're very thankful to have with us Dan Porpora today from Ball Aerospace. For those of you that don't know, Dan is a Mines alumni and graduated in, I believe, 06, 07, and has had a fantastic career with Ball Aerospace in the time since then, working on the James Webb Space Telescope and many more things. So I'll hand it over to him now.
Great, thanks, Jared. It's good to be back. It's been a couple of years since I've had a chance to talk to this group, and so last time I spent a lot of time talking about James Webb and systems engineering and what it was and what it means. And so I'm hoping to spend a little bit more time this time showing what I've been up to, how I got to where I am, some of the other things I've been up to, and we'll still touch on some of the cool stuff with James Webb. So now, of course, I need to figure out how I show my slides because I'm used to using different program. Start share as Zoom. Host is disabled, participant screen sharing. Gotta love technology.
One second. There we go. Now you should be good. Sorry about that.
All right, here we go. So there's that share button. There we go. All right. All right, a little background on me. The standard one slide kind of going through my life. I started off in New York, Westchester County, beautiful upstate, lots of trees, lots of water. Moved out to Boulder, went to high school at Fairview, go Knights. Spent some time actually interning at NIST, the National Institute of Standards and Technology. Talk about that a little bit more in a bit. Then went to School of Mines, again, 06 undergrad in physics, 07 grad degree in microelectronics materials engineering through the metallurgy department. And then I started working at Ball, and I've been working there ever since. So yeah, it's coming on 15 years now. It's been a long time. Certainly wasn't the original plan, but you know, it's been keeping me busy. So I've been working on a bunch of great programs: Glory Cloud cameras, OMPS, WSFM, JWST, so ozone mappers, weather mappers, cloud cameras, and JWST is the one telescope pointed away from the Earth, looking out at the stars. Along the way, I've gotten married, have 2 kids. Emmett just had his 9th birthday, and Harrison is 7. So that's kind of me in a nutshell. All right, great. That was a good talk. Any questions? No, just messing. Okay, so starting off, when I started my career at NIST, as I mentioned, somehow through my school managed to get a job working on web design for NIST. And there's a picture of me on the webpage I made back in the day in a white sweater. But as will tend to be a trend in my career, what happened to be a initial position grew quite a bit as time went on, and that's just something that just seems to happen again and again. So we started off working on web design, but while I was there and they're working on building up this lab, they needed help building frames for a pump system for all the vacuum chambers that they have. So roughing pumps, put frames together for that, piped them up, soldered a lot of copper pipes for them to bring the vacuum from the roughing pumps to the chambers. Started helping them with diffusion pumps that actually power the vacuum chambers and bring them to high vacuum. So learned a lot about that along the way. And then since I was working at the chambers at that point, then they started having me actually work with their MEMS devices and their micro cantilevers, taking magnetic measurements, working on terabyte hard drives, which back in the day was crazy. Terabyte, it's huge. So yeah, by the time I was finishing up my undergrad, I was an independent researcher, and had been published at the Journal of Applied Physics, which is kind of crazy to think about. But again, it's just one of these things where you never really know where things are going to take you when you start a position, and being open to opportunities can take you in all sorts of crazy directions. So you'll see this pop up again, but just that was the start of my career. And although I was really enjoying this, I knew I didn't want to stay there long term. Lots of reasons. Needed a PhD, but after 5 years of school, I was ready to actually, work and make some money. So I was looking for a job after I got my master's degree. I applied to Ball because it had a great local reputation. And wound up getting an interview because I had all this hands-on laboratory experience that I wasn't expecting to have when I first started the position, but wound up kind of falling into. And so they brought me in as an associate systems engineer working in advanced imaging. And as I quickly learned, advanced imaging is basically fancy digital cameras. So we work on star trackers. And so this is a pretty interesting thing to come across. A star tracker, fancy digital camera, takes pictures of the stars. It's got a large light shade that helps protect it from stray light. So you're not getting the sun or the moon impinging on the detectors. And you take some pictures of stars, and the onboard computer detects the stars, figures out where they are on the focal plane, and compares it to a star catalog, which is very different than a Sears catalog, but that was the first catalog picture that Google showed me, so I ran with it. So anyway, you look at the stars, you look at their brightness, you look at where they fall in the detector, you compare that with patterns that are known in the sky, and once you find a match, yay verily, you know where you're pointed. And if you know where your star tracker is mounted on your telescope, you know which way your telescope is pointed. So it's a kind of a helpful navigation tool back to the old days of sailing, where you used the stars to figure out where you were. So same general principles, just a lot fancier now. So working in star trackers was great. It turned out to be a fantastic place to start learning aerospace. And the reason being, the programs are small, cheap, and fast. And so something to take away from this is, when you have an opportunity to come in, if you have a chance to do something where you can wear lots of different hats and experience lots of different pieces of the job, it's really beneficial. For star trackers, I was involved in proposals, design, verification, testing, analysis, so all these different phases of a flight program pretty much simultaneously, because they were so small, they couldn't afford to have a systems engineer, even a brand new cheap systems engineer like myself, on any program full time. So you kind of piecemeal things together. So that was really interesting. I was just absorbing a lot of information, sitting in my chief systems engineer's office, listening in on phone calls, listening in on meetings with other engineers, figuring out what we're worried about, and then just asking a bunch of questions afterwards. So a great opportunity to learn. For me, though, Star Trackers wasn't a long-term gig because you needed a clearance to really dig into it, and I didn't have one. So I worked with my functional management to get me over to the star of the show, really, the James Webb Space Telescope. So for those who don't know what the James Webb Space Telescope is, it is NASA's next flagship astrophysics mission. It's the spiritual successor to Hubble. And it's bigger, it's badder, and it's looking at stars and galaxies that are much further away than Hubble could ever see. So for scale, looking at that left picture, you can see the teeny tiny people in front of the giant telescope. And that's what it actually looks like built. On the right, obviously, is a rendering of what it will look like in space. It has not launched yet. That's going to be October of this year, knock on wood. Things are going well, so that'll be fantastic to see it go up into space. But this is a monstrous machine, and its challenges were large. The technical details that went into this are absolutely amazing, and I'll kind of go into some of it. There's a whole other presentation on just the James Webb that we could do sometime. Happy to give it, but in the interest of time, we'll just kind of touch on a few specific things to give you a taste. For now, though, the way the telescope works is you have these gold mirrors, these hexagons, You can see all 18 of them. They point out in deep space, looking at stars, looking at galaxies, looking at things that are very, very far away. And it collects all the light and it focuses it onto this little mirror that's out front here. And that's the secondary mirror. And then that bounces the light into this center section, this black nose that again protects the science light from stray light from moon, sun, anything else that might try to get into the science instruments. And then the light bounces around inside there a little bit and goes to all the science instruments where we have cameras, spectrometers, and all sorts of interesting things to study these faraway galaxies and stars. So it's a big telescope, lots to it. What did we do on it at Ball? We got to focus on all the shiny gold things. So the primary mirror and the secondary mirror in particular. And then we've got a couple of mirrors inside this aft optic subsystem, this middle nose that we built as well. So showing you what one of these segments looked like. That's a picture of one of our team members checking out the mirror as it goes and comes out of a shipping container. Couple of things to note, couple of things to think about. One, obviously, it's gold. Why is it gold? It's because gold actually reflects infrared light really well. And one of the things that happens when you're trying to observe galaxies that are very far away is that you have to deal with redshifting. So just like the Doppler effect, when a race car drives by, you got the zoom, the sound stretches out as the vehicle is moving away from you. You get lower frequencies. With light coming from distant galaxies, it's similar, but instead of the galaxies necessarily moving away from you, what's happening is as the light from the galaxy comes towards Earth, it's actually getting stretched out because space is stretching out in between. So what was visible light starts shifting into infrared light. Infrared light is reflected by the gold mirrors very well, and that's why we have these gold-coated mirrors. Why do we have lots of small hexagonal mirrors as opposed to one big one? Well, honestly, something this size with current technology, if you tried to launch a single optic into space that big, it's gonna break. You can't do that. Again, current technology. But even more than that, you can't even stuff that inside the nose cone of any current rocket that's in existence. So you got to break it down into little pieces to stuff it into a rocket, fold it up, and then unfold it when it comes in out onto orbit and is ready for observations. So of course, although this side of the mirror is very pretty to look at, really all the interesting stuff is on the back side in terms of getting it to be able to unfold and align on orbit to act like a single mirror. Again, there's so many interesting details we can go into here. Some of the ones that we dealt with, I'll touch on. I'll actually start at the bottom. If you look at the back of this mirror, you'll notice all these holes that we dug into it in triangular fashion. We call it hogging it out. Because this thing is so big and we're trying to launch it up into space, we've got to get it as light as humanly possible. And we actually removed over 90% of the material of this mirror to lightweight it. And in order to do that, we had engineers assessing the thickness of every single individual rib on that mirror to optimize exactly how thin we could get it to minimize the mass, but still have it structurally sound to survive launch and be stiff enough to act like a mirror when it's taking observations. So that was a huge engineering effort. And then of course, in order to move the mirrors, you need motors. And so we put on what's called a hexapod. It's 6 motors, hexa, and that allows us to move each of these individual hexagonal segments in 6 degrees of freedom. We can move them in and out, up and down, left and right. We can tip it, we can tilt it, and we can clock it. So we can change exactly where it's positioned relative to its neighbors. And on top of that, we've got a 7th actuator in the middle here. And it's attached to these struts, which you see go to every single corner of the mirror. What that does is that gives us a 7th degree of freedom and actually lets us ever so slightly adjust the radius of curvature on each of these mirrors. So the issues we had on Hubble with radius of curvature, spherical aberration, et cetera, we don't have to worry about it because we can actually adjust the radius of curvature on each of these and get rid of any spherical aberration we see. Now, all of that, in order to make those work, you need electronics to power them. So of course, we've got electronics boxes that we had to build, which, oh, by the way, need to work down at 30, 20 Kelvin, so just above absolute zero, because we're running very cold out in deep space, and getting electrons to move at that cold is very difficult. So that was a whole other huge engineering effort. And oh, by the way, you need lots of cables to connect all those together, and those transfer heat, which you don't necessarily want. So that's a whole other effort to minimize the cables and minimize the heat transfer, but actually get all the electronics to work. So I mean, this is just our small piece of the puzzle, and the engineering detail that goes into it is just phenomenal. And being able to be part of the team was a lot of fun. And as a systems engineer, being involved in all the interfaces of things, it was a great opportunity to just learn about a whole bunch of different things. So one of the ways that I was able to do this was through what's called systems modeling. And so this is kind of how I got a good sense of all the different aspects of the program that we had here at Ball and our pieces of it. I was responsible for trying to figure out where we're going to put each of these 18 mirrors. If you imagine, we've got 3 different what are called optical prescriptions of mirrors, A segments, B segments, C segments. They're all a little bit different based on where you put them on the backplane. So you can see that the A segments all go in this middle section. The B segments are further out on the outer ring, and then the C segments are kind of in between. But although the A's and the B's and the C's are all different, the A's themselves are all interchangeable, the B's are all interchangeable, and the C's are all interchangeable. So which one do you put where? If you do the math on it, it's 6 factorial different combinations times 6 factorial times 6 factorial. That's 373 million possibilities as to how you can arrange each of these 18 primary mirror segments on this telescope. And figuring out where to put which one and what the best position is an interesting question, because really, how do you define best? First off, what is best is dependent on what criteria you're going to put down. And working with the team, we decided that although we have these motors to move the mirrors around into different positions, really we want to minimize the amount of motor usage we have. We want to maximize the amount of range that we have available for each of these motors. So we want to put the mirrors down in such a way that, based on all the different known manufacturing errors, both on the places we mount the mirrors and the mirrors themselves, that they're all as close to perfect as possible in terms of when we unfold everything, everything is as close to nominal, as we'd say, as possible. So how do you go about determining that? Well, you've got to look at all the different error sources that can go into manufacturing a mirror or manufacturing the mounts onto which the mirrors mount. And for that, you need what's called a technical budget. And we made an actuator range budget, and this was my responsibility over many years on the program, was building this, expanding it, and refining it. And so you can kind of see here on the left some examples of the different error terms that we would have to track. Prescription alignment fab. So how well did we actually polish the mirror relative to what we wanted to polish it to? How well are the alignment references? So we measure everything relative to what are called tooling ball holes or fiducials, a way of measuring other things on the mirror to a known point in space, but those known points in space have some manufacturing error on them, so you got to account for that. How well can you deploy things? What are manufacturing errors in what's called the conic constant, et cetera, et cetera. So you can see that that's those, I don't know, dozen rows represent just a teeny tiny piece of one sheet that we built, one for every single mirror on the entire telescope. And for all four, well, for all 6 degrees of freedom that we can move the mirror. And we tracked all the known and all the unknown errors and smushed them all together in the spreadsheet. And filling this out was a really interesting experience because I've got to talk to the structural engineers to understand the errors that come up due to vibration and how things are going to shift around. I got to talk to the mechanical engineers about the tolerancing on the drawing, and the machinists about the tolerancing on how well they can drill the holes, and talk to the thermal engineers about how things are going to shift when we switch between hot temperature and cold temperature, and talk with the electrical engineers about how much power they're going to wind up putting into each section of the mirror, and is that going to cause a distortion because it's going to heat up, and now I got to go back to the thermal engineer and talk to them about it. And if you hear background noise, I apologize. One of the joys of working from home, we do have my 2 kiddos running around the house. If it's getting distracting, let me know, but otherwise I'll just keep pushing. So that was a really long experience. It was very tedious, I'm not going to lie, but I got to talk to a lot of really smart people, read a lot of papers, ask a lot of questions, and learn a lot about the system and how everything worked. And so this wound up being a great experience. And what the program got out of it was a map of our optimal installation, which the program wound up using. So, you know, I'm a couple of years out of college, and there's a $10 billion telescope where the mirrors are installed where I told them to put them, which is, I don't know, kind of weird to think about. And you run all the math, you look at all the different options you have, and we were able to, you know, beat down the errors down by either 4% or 8%, depending on how limited you are in which mirrors you're allowed to place where. And so that was a great answer for the program. We were able to reduce the technical risk and figure out the best way to do things. And so that was a lot of fun. And that's one of the big things systems analysts get to do, is to really think about problems in a systematic way that cross boundaries from different engineering disciplines, and ask all the questions and try and make the best end product for the user. And then, of course, for me, I got to present it at Montreal and SPIE, so that was cool. And then we came back and we worked on it some more, and we made even better predictions. And now not only do I know which mirrors go where, but I can tell you within a certain error bound where they're going to end up on orbit relative to where we want them to end up. And I can show analytically that we're meeting all our requirements and that our corners aren't going to crash into each other. And we even now have just nominal deployed states. We're not going to just go to our 0 position. We're going to go deploy each of these mirrors to where we think the best aligned state is. Save ourselves some time with the commissioning process and hopefully make our lives easier. And so that was another great thing we got to do for the program, which was a lot of fun. And of course, I got to present that at Edinburgh in 2016. So lots of fun there as well. All right, so that's a lot of the work I did on James Webb, the technical stuff, and there's a lot more we can talk about. But kind of switching gears a little bit and taking it into the career path discussion. While I was working on all these technical things, one of the things that I kept doing that worked out well for me is I would constantly be on the lookout for any opportunity to do additional work to help out the program, anything that would stretch my capabilities, especially if it was of importance to my lead. My lead was worried about it. obviously I made it something that I was worried about, and did my best to help her out. So some examples of ways I was able to stretch and help and grow my capabilities. I developed a risk management system for the program, which the company wound up spinning off to other programs. I mentored co-ops and a handful of interns over the years, which was a great experience in terms of being able to lead a small team of 2 or 3 people, and how to work with others, and how to manage others' times, and how to split out work and delegate, et cetera. Uh, develop customer slides for the manager, and then after that, the program manager, which, by the way, pro tip, um, making slides for your boss is great because it gets you into meetings with higher ups and customers. Because when your boss can't present those slides, guess who knows them better than anybody else? You do. And then you get to present them. And getting FaceTime with customers is just invaluable, growing that network. And I started doing non-technical stuff with cost estimating, scheduling, and budget tracking. I didn't think I'd have any interest in that, but I was decent at it, and opened up a lot of doors down the road, as we'll see. Spoiler alert. But because I was taking on all these responsibilities and I was helping out in a variety of ways, that wasn't just a systems analysis role. I was eventually asked to be the deputy SE manager. So I was taking on those responsibilities more formally. And after a little while, the deputy title was dropped, and I just became the systems engineering manager for James Webb, which was really exciting. But this was 5 years into the program. And after another 2 years of being the SE manager, I'd been there for 7 years, heads down, and really didn't know anything outside of James Webb. I'd been at the company for maybe 9 years at that point, 7 of which has been on that program. And I was feeling comfortable. I knew everyone on the team, both internal to Ball and on the customer side. And I could do everything I needed to do very quickly and efficiently. But I recognized it was time to start being open to opportunities. Even though I had plenty of full-time budget, plenty of work to do, I wanted to be open to new things, to continue growing and learning. And so invariably, something popped up in what's called functional management. Position was open for a deputy manager of the mission architecture group. So when you get into aerospace, lots of companies are what are called matrix organizations, which means that you kind of have 2 bosses. You have your day-to-day program team, and your program boss, the program manager, your systems engineering manager, or your engineering lead, whoever it is, with day-to-day tasking on the program you're working on. But then you have functional management, who's sort of the in the background, responsible for finding all of the systems engineers, for example, or electrical engineers, or what have you, maintaining a stable of those individuals, making sure that they're paid well, understanding whether we need to hire some, promote some, training, assigning which systems engineers go to which programs, et cetera. So it's as far away from technical as you can possibly get. It is all just worrying about people. But it's something that would stretch me, I knew, in a very different way. And I had kind of a small taste of it when I was leading interns and co-ops, and I enjoyed that. And I thought, all right, well, I'll give it a try, right? It's going to give me exposure to upper management. It's going to give me exposure to other programs across the company. Again, having spent the entirety of my time on one program, being able to step back and see what else is going on, and making connections across the company, I knew would be a good thing to do. But it was scary. Certainly something completely different than I've ever done before. Certainly wasn't something I was planning to ever do. And on top of it, my job would be managing a group of really, really smart systems engineers who knew their job way better than I did, had many more years of experience. But it's unique. This was an opportunity that wasn't going to come around again for any time soon. So I thought about it a lot. And as with any of my career choices that I've made along the way, I spent a lot of time doing fact finding, which means I spent a lot of time talking to people and asking their opinions. So I spent time talking current managers, how they like the position. I spoke with people who had done it in the past, what they thought about it. I talked to my peers. I talked to people who were on the program side just to get a feel from a lot of different perspectives what people thought about it. And once I had a good sense of the job and I had a good understanding of what the pros and cons were, I could make a much more informed decision. So I took it, and I wound up enjoying it. It was a lot of fun. And I got a pretty unique opportunity in 2016 to actually write my own job description because the functional department went through a reorganization, and they needed help with hiring and they needed help with onboarding folks who were just out of college. And so I got to basically build my own little mini department um, because I just happened to be in the right place. So I mean, certainly luck there, and I'm glad I took the opportunity. So now I've got a lot of background in systems engineering, strong technical background. Now I've spent a couple of years working in functional management, which is purely people management. And that's an interesting combination where you're really prepared to take on something like a program manager role, where you are managing people on a program. Um, as it happened, the program manager for JWST back in 2018 moved on, and she wanted me to step into her shoes because of all the support I'd given to her as a PM when I was working on James Webb, and because of the non-technical support or non-technical abilities I've demonstrated through functional management. And now I've got a whole new job to learn. And so I got to continue my interactions with upper management, meet with the customers again, and just kind of see the program from a different perspective. As I mentioned, the PM role is pretty interesting because it is a balance of the technical and the non-technical, really pulls together a lot of the background that I have. And I'm still learning the ropes. So I don't expect to be comfortable anytime soon. So we'll see how it goes. But yeah, that's kind of where I am right now. So what are my takeaways from all of this, and what are words of wisdom I would give? I would not spend too much time plotting out your 10-year course, at least from my experience. And it's just one example I understand completely. You're not going to be able to predict what opportunities are going to come your way 2 years from now. It's going to be impossible to predict. Things pop up. And so what I would recommend always being on the lookout for is, over the next 2 years, what's going to give me the most opportunity to learn and grow? It may not be exactly what you were thinking of. It may not be exactly the career path you were thinking of, but if it gives you an opportunity to learn and grow and expand your skill set and expand your horizons and meet different people and grow your network, that's probably going to be the way to go. Ask for help, ask for clarification, ask for exposure, ask out of curiosity, just ask questions, constantly be asking, constantly be learning. I mean, that is the that's the most valuable thing you can get, is knowledge along the way. And so just constantly asking, not being afraid to ask. It's certainly something that's proved invaluable at Ball, and hopefully any other company with an open culture of learning and growing. Under promise, over deliver. This is a great one. You can't always do it, but whenever you can, I highly recommend it. If someone asks you to update a spreadsheet, you think it's going to take you a day, ask for a week. A couple of reasons for this. One, as humans, we always underestimate how long something's going to take. You get better with it over time, but it's something that everybody always underestimates it. I do it too all the time. So Anyway, you think it's going to take you a day, you promise a week, you wind up spending 3 days on it because of course you run into problems, but then you can on the 4th day, let's say, come back in fresh-eyed, check it for errors, give it a once over, clean it up, and maybe even do a little bit extra. If you're working on spreadsheets, you can put in a couple extra graphs or data analysis or do something above and beyond what was asked of you. And now at the end of day 4, you've delivered something early that was beyond what you actually said you were going to do. So now you're a hero. And anytime you can give yourself the opportunity to be a hero is a good thing. So under promise, over deliver. Any opportunity to get face time with the customers, again, getting exposure, getting recognition is going to be really helpful down the road. It's going to help you find your next job, whether it's within a given company or not. Just making connections and having people know your name winds up being invaluable. As I've mentioned a couple of times, be open to helping out on something different, something that isn't necessarily within your job description. Anything that is going to be of importance to your boss should be of importance to you, because really your job is to make their lives easier. If you're not making their lives easier, why are they paying you? So, just be open to it. And especially if it's going to be something that grows your skill set in a different way, just give it a try. If you don't like it, that's fine. But, you're not going to know unless you give it a shot. And of course, if you're feeling comfortable, it might be time to move on. Because if you're comfortable, that means you're not pushing yourself necessarily. And if you're not pushing yourself, you're probably not growing as fast as you could. And regardless of anything else, whether it be job title or a specific step on a perceived career path, just having that knowledge and having that exposure is going to wind up being more valuable than anything else. So that is what I've learned over the years. And I hope some of it's beneficial. I hope some of it's been interesting too. And I am happy to take any questions that anybody may have.
Yeah, I had a quick question. I put it in the chat earlier, but I wanted to kind of explain it more. So when you were calculating all of the possible orientations for like the mirror tiles, how do you start, like what are you even looking for when you're calculating? I guess like with a problem that big, I just wouldn't even know where to start, honestly. So I was just confused how you got to a solution.
No, absolutely. And so what you're seeing here is after many iterations of it, as with any time you try to eat an elephant, you just got to start one bite at a time, right? And so a lot of it came down to, okay, we need to make sure that when these mirrors are deployed, we have enough actuator range that the motors are able to compensate for any error we may throw at them. Otherwise, why even bother having these motors on them? And it just starts off with a brainstorming session of, okay, what are all the errors? Let's look at the integration flow. Let's look at the test flow. Let's look at every measurement we take and just say, okay, here's a measurement, here's a measurement, here's an integration step, here's a manufacturing step, and you just list them all out. And you say, okay, you assume that there's going to be errors in every single one. And then you just start going line by line and saying, okay, how do we understand these errors? How do we cap these errors? How do we manage these errors? And you just slowly go down the list and you work with all the team members and you ask questions and you iterate. And every time the plan changes, because the plan is constantly changing, you adapt and you adjust. And as you learn more, you update. And so it's just it's a slow iterative process. And I think the way we started it was just to say, okay, let's just write down everything we can think of, and then we'll take it from there.
All right, that's awesome. Thank you very much.
Yeah, absolutely. And obviously the other answer to that is I asked people who had done it before, how they did it and what sort of formatting they did and what sorts of tools they used. And I didn't invent the spreadsheet system. I stood on the shoulders of giants, and again, just asking those questions and learning from that experience. That's always going to be helpful. So, yeah. Wait, I'm going the wrong way. Back to that one. Okay.
So I was wondering if there's any experience or whatnot that you wish you would have done or had in college going into not your specific career, but the field in general, because you can't, like you said, know every twist and turn that's going to come up.
Absolutely. I think, what do I wish I had more of? In my case, honestly, I wish I had a little bit more aerospace specific knowledge, because it made life a little bit easy, a little bit hard coming into the industry, not really knowing anything about aerospace and just having a purely physics background. So that would have been helpful. But honestly, I'd say, thinking back on it, probably the most helpful thing would have been a little bit more stats and a little bit more of finance. Because as much as engineers like engineering, at the end of the day, money matters. And so having a basic understanding of what everybody's complaining about you spending all of their money on, and what is they're worried about and how they're worrying about it, is certainly helpful. And then having a sufficient understanding of statistics to understand error terms and be able to sift through large amounts of data and distill it down is actually extremely helpful. So I guess I go with finance and I go with stats would probably be the two. And of course, any project group, any project work, any lab work, anything you're working in a team is always beneficial.
I have a question.
Yes, ma'am.
Do you have a favorite experience with working on the James Webb Telescope? Like, did you get to go into the clean rooms and everything?
I did. I was pretty lucky. The optical portion of the telescope, this picture right here, as you see it here, we took it down to the Johnson Space Flight Center to test it down at cryogenic temperatures. And we put it in the giant chamber A, and I got to go in there while they were in getting things set up for test. I was on shift while we were doing testing it down at Johnson, and being able to see it was pretty cool up on the stand. And then of course seeing it put together in the clean room over at Northrop was pretty amazing as well. In terms of the specific experiences working the program, it's hard to pare down 7 years to a single piece of it that I enjoyed. Really just working with the team on all the different complications and solving all the different technical issues that came up along the way. It's all been a blast, really. So yeah, I'm really glad I got to spend some time on this program. I'm very excited for October.
Cool. And then you said your degree's in physics?
Correct.
How did you know you wanted to do physics versus like mechanical or electrical engineering?
Sure. The way it came was completely unrelated to aerospace. Originally, I was really interested in chip design, like computer chip design. Being a bit of a computer nerd myself, growing up, I was the kid who built my computer from boards and chips, and usually had my computer strewn about on the floor, and sometimes could put it back together. As I got older, I got better at it. But anyway, I was interested in that, and talking with folks, I was learning that electrical engineering, while helpful, when you really got into the design of the chips, it was getting so small that you needed to understand quantum dynamics. And so knowing that and knowing the breadth of applications that physics has, I thought that would be a good way to go. And then, of course, I got my master's in microelectronics materials, kind of leading into that. Both chip design and solar cells, both I became more interested in that as we went. But yeah, physics in particular wound up being really great because any problem I came across, I could always ask enough dumb questions that eventually I could get it back to the first principles. It just took a while sometimes.
Cool. Thank you.
Yeah.
Well, if no one else has anything, kind of a follow-up question to what you talked about with finance.
Yeah.
How much of our if we were to go straight into industry for large corporations like this, how much of our jobs would we have to be expecting to like worry about that versus the more sciencey and technical pieces?
Sure. I can tell you from working at Ball, at least, again, every company is a little bit different in how they operate, but it runs the gamut, right? You can spend all your time like I get to now, worrying about cost and schedule, or you can really dive into the technical stuff and not really be bothered by it. We've got people who are the world-class experts at dynamic loading or wavefront analysis, and they spend most of their time working on their technical issues. But again, at the end of the day, it's something that's going to pop up. The question as to whether or not it's worth the cost is going to be a question that comes up. So, 5% of your time, especially early on, generally speaking, you're not expected to start doing cost benefit analyses for things if you're an engineer. But having that background and understanding and being able to appreciate where the managers are coming from when they're asking these questions and what they're worried about can at least help you frame how you describe things and how you explain things to people in a way that makes sense to them. But no, you can get away without actually really having to worry about it for a while, probably.
Okay, good to know. The other question I had was, since you've obviously enjoyed your job, what have been some of the benefits and drawbacks to working at larger companies? Because there's so many things we could do, and big companies are, not. There's not too many of them to choose from. So what would you say about that?
Sure. And Ball's interesting because, we're 4,000 people, which is huge for us. It's bigger than we've ever been. But, compared to Lockmart or Northrop or some of these other behemoths, we're tiny. But no, we're not a garage shop of 10 people. So it's one of these things where it kind of depends on what you're interested in. There's pros and cons either way. Having a larger company certainly gives you more stability, larger support structure, and usually there's benefits to go with it in terms of finding groups of people that you want to socialize with and work with and learn from. There's usually more opportunities for classes and things of that nature versus a smaller company where you're more on your own. But a smaller company is going to have a lot less oversight, for better or worse, and that's probably a lot less process, for better or worse. And so if you're looking for creativity and freedom and an opportunity to just kind of go hog wild on something, the smaller company is going to give you a lot more of that versus the rigor you're going to see at a larger company. So my experience with Ball obviously has been positive. I've had the support that I've needed, but still the flexibility to kind of do what I want and kind of go dabble in different things. So I've enjoyed it. Again, different personalities are gonna run into the processes and just think they're completely overbearing. And there are going to be other people who would come to ball and say, oh my God, nobody's actually telling me what to do. I don't know what to do. This is really too stressful. So yeah, it's not an easy answer. It's really dependent on you and what you're looking for and what you need. Everybody's different.
Yeah, definitely not an easy answer, but that does actually help a lot. So thank you.
Yeah, absolutely.
Well, if no one has any other questions, thank you all for joining us today. Thank you to Dan for taking time out of your day and your evening with your kids. It does mean a lot to us.
No, absolutely my pleasure. It's always great to speak with you all, and I'd love to be able to do it in person sometime. If you ever have any questions, want to reach out, feel free to email me. Jared's able to get in contact with me. And yeah, hopefully we'll get to see everybody in person eventually.
Won't that be the day? Yeah, so thank you all for coming. If you have any other questions, feel free to stick around for a few minutes and we'll be here.